So good afternoon, everybody. Thank you for joining today. We have with us Dr. Mrityunjay Doddamani. He is currently Chairperson and Associate Professor at the School of Mechanical and Materials Engineering. Previously, while he did this project, he was at NIT Suratgal. Currently, he is at IIT Mandi. And I can see lots of affiliations. I think you will introduce yourself, Doctor.
Yeah, sure. Quickly, I can go through. Yeah. Shall I start?
Yeah, sure.
Okay. Yeah. Thanks, Dr. Roshni, for this is a nice initiative as a webinar series for ISHRAE funded projects. So I'm Mrityunjay. I am presently Associate Professor in School of Mechanical and Materials Engineering at IIT Mandi. I'm also presently heading the school. I am also affiliated to New York University for my various research activities. Yearly once I do visit there as an affiliated faculty at New York University, United States. So before talking about the ISHRAE project, which was sanctioned to me in 2020, I will just give you a brief introduction about what all I do. I am basically a manufacturing engineer, nothing to do with the thermal sciences, because as we all know, in mechanical engineering, there are basically three verticals. One is manufacturing, second is design, third is thermofluids or thermal engineering. And now there are many interdisciplinary areas are coming up. So I belong to manufacturing sciences, and I am working on making from virtual to a physical domain conversion is my area. So with that manufacturing base, I work in conventional and advanced manufacturing. That is what the first, I use pointer, sorry. So this is what is that first one represents, wherein conventional and advanced manufacturing is been dealt with. And then rest all are the areas wherein I am working with advanced manufacturing with Industry 4.0, then 3D printing precisely, then cybersecurity and additive manufacturing, because additive manufacturing is typically a digital manufacturing platform. So how to make these files which are being transmitted over the intranet, or how to make them hack proof, because in additive manufacturing, as we are heavily dependent on 3D printing, a small change in parameter may introduce a localized defect, and defect need not have to be defect like a void. It can be a same material getting deposited but with a different property. So how to make sure that the files are been hack proof, that is the area. And then extended additive manufacturing to solar cells as well. And all these projects are funded. So this is my broad area of working. My research group works in sustainable foams or syntactic foams for that matter. That is this region. I do work in healthcare. I do work in energy harvesting systems as well. For all this, the core is the manufacturing, and I'm into sustainable manufacturing now. And here pertaining to foams, this is where I got connected to ISHRAE, though I am not from thermal sciences. So presently my group is being funded for 40.79 crore from various funding agencies. So just before going into the ISHRAE project of foams, I want to just talk about foams a little bit. This is the area wherein I'm working since last 10 years. And my PhD was also in the same area. So we call it as a foams. Foams are basically two types. One is a closed cell foam, second is an open cell foam. So this is a typical picture of an closed cell foam, wherein in any material, we infused hollow microballoons. And by infusing these hollow microballoons, we take an advantage of that to the tune of even going for an insulating foams. So here the benefit is we can have a different size microballoons, different wall thickness, because these are hollow, thereby the wall thickness comes in picture. So based on the different size, based on the different wall thickness, the property of a given, we call it as a foam or a composite for that matter, changes. So we have an additional axis, and that is the wall thickness, and that's what has been shown here. We can have a same microballoon outside diameter, but inside diameter keeps on changing. And these different inside diameter gives us a flexibility of developing or designing a material. from underwater vehicles or from marine to automobile to aerospace and space. And this is what that flexibility has been given by such micro balloons having the same outside diameter but different varying inner diameters. And this also
But what would be the material of these micro balloons?
Yes, yes. So naturally, fly ash, which is a outcome of our thermal power plants, is one. Second, there are artificial ones are also present, like glass microballoons. These are commercially available, relatively inexpensive. Fly ash is a natural one. Then people have worked on silicon carbide, aluminum oxide ones also, and with the different shapes as well, based on the application. But from as far as the strength and other property enhancement perspective, we will always go for an spherical ones because there is no stress concentrator, and even in which we infuse this, there will be an uniform spread because of the spherical in shape. And this is how these microballoons gives us a wide flexibility. Applications are numerous presently available, starting with the thermoforming plugs, which are being used to form different metal sheets. Then underwater maintenance modules, because here buoyancy is critical, and that's why for any given material, by infusing these microballoons, we cut down the density, and that is why the lightweight materials comes in picture. And the material into which we can infuse is from polymers to metals to ceramics as well. Submarines do use. Then in our extracting the crude oil from the somewhere at the end, far off from the shore, to bringing them at the shore, we transmit them through pipes, and these pipes sink, and that's why these buoyancy modules have been developed, which always floats on the seawater and doesn't make this pipe to sink and rupture it in between. And then there are many other applications in railways, aerospace. And instead, there are some interesting applications like this also. I think all of us can easily make it out. This is a football. So in sports, these foams are quite widely used. So in 2000, way back in our World Cup football, we took a ball and we just cut it out. And we wanted to see what Adidas has done innovation in this football. Basically, this is a plastic ball and not a leather ball. So what did we found is there are different layers. And here, this is the outer layer, which is a polyurethane. Then comes the closed cell foam, wherein the micro balloons are being infused here. This is a small layer of that. And then there is a large layer of higher thickness layer of open cell foam. And open cell foam are nothing but wherein the porosities are interconnected. A scotch bar in the kitchen is typically an open cell foam. Sponge is an open cell foam. And this has been engineered in this football. And why this has been engineered, it's basically a very well-known reason. What we can deduce is such a large sponge is required, because when the player gives a header, there should be minimum injury to head. And that is why this large open cell foam is induced. And there is a small layer of the closed cell foam is also there just below the skin, so that it will absorb the moisture, keep it locally available, and it will not allow this moisture to seep in inside this compress or inside the air or inside the bladder, which will gain the weight and then change the directions or a flight of a ball when it is kicked. And there are many other applications also, like the soles of the shoes, and that is why such shoes cost more, because we have induce these open cell foam, closed cell foam combination of that, so that we can have a minimum jerk to knees. So this is how the basically syntactic foams are being quite extensively been used from buoyancy, marine, aerospace. And here comes my interest because of syntactic foam, and wherein I approached ISHRAE way back in 2019, and 2020 I got that project on insulating foams. So here basically, when we talk about buoyancy structural applications, we use different material system, we design different materials, and that's how the cost is not a matter much. But whenever we go for a large scale industrial applications, cost is a sensitive matter. And that is where we design a material and then come up with different ideas to make it foam structure.
But there's such a wide spectrum of materials, no?
Yeah.
Because your applications are numerous and their different properties also would be different. So it's a huge, spectrum from which you have to choose.
Yes. Yes, you're absolutely right. So if I'm going for aerospace or space, I need to choose a different material system and look around how I can design a material, tailor a material. Because when I say, when we design a material system for a specified application, can it be let us say, a single material or a combination of a material? And when we say combination of a material, based on strength and modulus and whatever properties you require, there are again different strategies that comes in picture. Like, do I need to have a coating so that it can be hydrophobic, hydrophilic? So likewise, we go on devising different strategies when we design a material system for a specific application. And the spectrum is very, very wide, and this is a bigger market, a biggest market rather for syntactic foams in that sense. So this is one just simple slide I just put in. If we just talk about high density polyethylene, which is very widely used nowadays, which is one of the thermoplastic, how does it matter if I try to say 1 kg of that particular virgin polymer or even a recycled polymer? So this is what our research group's other aspect is. Can we able to make it more sustainable, try to cut down the consumption of virgin or recycled polymers by infusing such foams, or rather some foaming materials like these tough shelled ones, or even we can infuse the gluing agents in that case. So again, as it has been very clearly understood, what is your objective? So this was one such objective wherein we did develop different materials for all the plumbing applications, electrical applications, wherein the load bearing was not an issue. It was not a no load bearing element. Moisture absorption, not much. So that's how we developed a fly ash based system here for all these electrical applications. So that is what this slide shows. This is what our research outcome is, our group's research outcome is. So this is one such a block of syntactic foam. Now you all know what I mean by syntactic foam. We infuse hollow micro balloons inside the system, and it can be hollow micro balloons. Once it goes in the hollow micro balloons, we call it as a closed cell foam. And if we interconnect these porosities, it becomes an open cell foam. But this is closed cell foam, and the size of this is around 1000 millimeters, 1000 millimeters by 300 millimeters. Such blocks presently India is importing from the United States, France, and UK. And this is for specific defense application. We did in-house manufacturing of this, and we are supplying it to Ministry of Earth Sciences. They in turn will supply to NIOT, and that will be deployed by Indian Navy in the specific applications. So these are the blocks. The intention I shown this is we do not have an issue with the scalability. We can definitely go for scalable applications. And this is what I was talking about, a fly ash based system, a closed foam system, which reduce the carbon footprint, even the plastic consumption itself by 10%. This is another one. This is the nose cone of submarine, remotely operated small scale. I can't tell you where it is presently deployed, but this is again used for defense applications, wherein the weight of such the cone of this what we developed is 1/4 now as compared to the present one. And there are some gaskets here. So oil and natural oil industries, wherein they use a different metal gaskets. We replace that with a polymer gasket with a specified foamed system. This is a screw for biomedical implants. Again, this is biodegradable and so on and so forth. This is another one wherein we filed a patent, and also this will be funded soon by DRDO. Anybody can immediately make it out what is this. This is a hammer of a small weaponry system. And when we talk about small weaponry system, it is 9mm machine pistol to AK-47 to 51. So the requirement was, can we reduce the weight of small weaponry systems for a soldier who is in the Siachen glacier? So 1/6 we reduce the weight. So we replace the metal with the plastic. And again, that's a foamed system. We did some innovation in 3D printing. As I said, my focus is on conventional and advanced manufacturing system. So in 3D printing, because it deposits layer by layer, Z strength is an issue. So we address that Z strength issue also by modifying the basic system. So this is a novelty diagram of syntactic foams, which my group specifically does. And this is where I got connected to ISHRAE. And thankfully, I'm thankful to ISHRAE that they funded, though I am from manufacturing background. So I still remember in Delhi, there were around 30 projects being screened, and out of 30, 29 were from thermal background. I was only from manufacturing, and only one project got funded. Thanks for that. So I'm going to the foams and now the ISHRAE project. So this was that project wherein the title was Cost-Effective Enhanced Insulating Foam for Cold Storage Application. So from ISHRAE, Yash was the point of contact. And this was the typical timeline when it got funded, approved in 2020 and completed in 2022. It was a 2 years project.
But the
So
COVID, I think COVID interfered a lot with this
Yes.
project. Yeah.
Yes,
Yeah,
yes,
yeah.
ma'am. Yes, ma'am. Very much true. So this was what the timeline at that time. So the deliverable of this project was a new product with a better insulating capabilities, upscaled process, and easier adaptability. Now, easier adaptability to both conventional and advanced manufacturing systems. And that is why I kept that one of the deliverables while looking at that, because having a domain expertise in conventional manufacturing and working in advanced manufacturing, I thought that we should be able to develop a material which should be easily adaptable to both these systems. And this is what was the flow of investigation we executed at that time. So we started with the CFD simulation, and the basic reason for the CFD simulation is to tap the effective thermal conductivity of a lightweight structure. And that is what we did here in a simulation environment. Then we did an analytical investigation, took the effective thermal conductivity, the volume of a Kelvin structure. What is that Kelvin structure? I'll come back a little later. We can make it out through this as of now. So we took the effective thermal conductivity from the simulation and then went ahead with, we need to find out the enclosure volume of this structure, what we have designed, so that the thermal conductivity can be tuned. And then we did an analytical investigation. And after the analytical investigation, we actually manufactured the component and then shown the actual product outcome of this entire research flow. So this was about this. About this, the first one in CFD simulation, what we did was we did a pore level simulation. We took a unit cell and then try to find out the effective thermal conductivity. And for the porous structure, we chose the Kelvin structure, which is the best as far as the thermal conductivity perspective is concerned. Then we modeled that. We took a cubical enclosure, we just modeled air surrounding it, and then followed methodology and generated the grid mesh, and then finally did the pore simulation. This is how that Kelvin structure looks like. These are a single unit cell of Kelvin structure. We varied the porosity level also, because this porosity level plays a very vital role for the heat to take a specific path on the struts and so on and so forth. So we varied from 70, 80, 90. We did the simulation. We applied the boundary conditions using steady state thermal condition, hot plate and cold plate. And then we maintained 100 degrees C at one end and 25 degrees C at the another end, because we wanted to know what is the heat flux through this structure, which is a Kelvin structure. This is how the Kelvin structure looks like. Small, all are these struts. These are forming a hollow space again. And why hollow space? Already I mentioned it. Being in syntactic foam area, I know that how we can make this hollow space to be beneficial for different applications. We did the simulation and then all these results way back in 2021, I guess. Then we took from these all simulations, we wanted to know the enclosure volume. What is specifically the Kelvin volume? And then using an empirical equations which are available, we found out the effective thermal conductivity. Then we compared the effective thermal conductivity through simulation and theoretical means. These are non-foamed ones, and this is a foamed one. So when we say non-foamed, meaning all these struts are made up of a solid material system. And here, when we say foamed, the strut itself is a foamed one. Now, before going into the manufacturing side, we wanted to know what is that level we can reach. I'm sorry, with the porosity level increase. And when we compare with foamed and non-foamed, the theoretical values are somewhere around 0.03. Was what we estimated using our simulation and analytical background. And then we used a 3D printer again, as Dr. Roshni rightly pointed out. This was work when I was at a National Institute of Technology, Karnataka, Suratgal. So this printer was readily available at my end at NITK, which was funded by a DST project. This printer has a build volume of 500 millimeters by 500 millimeters by 500 millimeters, open source. So any material I can use, 3 years warranty. So in these 3 years, I just used whichever materials we wanted. We never brought any material from the market, a ready-made material from the market, in the sense this is known as a FDM, or fused filament fabrication. Input is a filament here. Its filament is nothing but a wire. So polymer wire is been fed, CAD drawing is fed, and then it prints layer wise.
But when you have hollow spaces, what is there inside the hollow spaces? Because I mean, you said foamed and non-foamed. I presume foamed means you have a foaming agent, right? When it's non-foamed, then you're forming it in your 3D printer. So what is the void is containing?
Yes, the white trypsin. I'll come back to that, ma'am.
Yeah.
When I show the pictures. So here the filament is being fed. And all these filaments, we never bought it from the market. We brought the raw material, we extruded the filament, and that's how the ISHRAE project has funded one equipment known as a twin screw extruder. And through that filament, we printed on these 3D printers. It's a completely open source system. And you can just see what is the printing temperature, which I go here. It is up to 450 degrees C. Generally, 3D printers are available from 15,000 onwards, but they have a limitation on build volume, material usability, and typically this printing temperature, which is up to 250 degrees C, sometimes 280 degrees C. So then, based on our simulation background, analytical background, we printed different structures. So here you can say this is an open cell foam. This is a gyroid structure, which has been basically used for all structural applications. And this was what our interest was. It's a Kelvin structure. So what we looked into in the simulation, same has been replicated through a 3D printer here in the form of an Kelvin structure. And I have just zoomed out, and you can see an actual Kelvin structure here. So these struts are solid or foamed. That is what non-foamed and foamed means. And this is how the Kelvin structure looks like. I'll repeat. The struts, the joining elements which form this Kelvin structure, is either a foamed one or a non-foamed one. Then we did experimental measurements on thermal conductivity as per the ASTM standard. So with Kelvin structure, these are non-foamed ones, please. So all these struts are solid ones. We could see at 90% porosity. So 90% printing is also possible. Now, why I am saying 3D printing here, I believe all of you might have easily understood, because in conventional manufacturing, producing such Kelvin structure is, as of now, not possible.
Yeah.
Right. So this is where advanced manufacturing system comes in picture and helps us in achieving a high level of porosity as such. So, this system was funded by ISHRAE. So this is twin screw extruder system. There are 2 barrels here, and this is a parallel type. So there are 2 types of twin screw extruders. One is parallel, another is a conical type. Conical type we go when we induce metal powders in the polymers, and because we need a higher thrust and pressure. But here, as we were not intended to go for any metal powder system, we went ahead based on our domain expertise. We said parallel screw is sufficient. So this is a parallel screw system. So what we do, we put the pellets. Pellets is small granules. Here we use the polylactic acid, PLA. with supercritical carbon dioxide, SCO2, that we mixed here. And then we set the temperatures. Here is the typical barrel system. In this, there are twin screw meshing with each other. Materials been fed here. There are 3 heating zones. So most critical in all these manufacturing systems is what speed of screw you set, what temperature do you set to get an appropriate foaming element. And this is where in experimental systems investigation, it takes quite amount of time, around 6 months time, to optimize, to look around, to revisit and come back with that optimum structure. So what does this machine gives is we give an input of pallets and whatever reinforcing or additives what we added here is the input, and output is a wire. This wire of a critical wire of a specific diameter is very critical in 3D printer system, because here we have a filament as the input. So here we have only plus minus 50 microns. Variation is possible for a printer to just feed it appropriately. So the diameter management is also very critical, and then temperature at which we keep the water. So a lot of experimentation goes on here, and this is what the complete picture of this project is. So we went ahead with polylactic acid with glass fiber, hollow micro balloons, and then also with the SCO2. So we mix this, we get filament. This is a twin screw extruder. But in this twin screw extruder, there is one, because these are all machines, they have specific limitations. Twin screw extruder doesn't give a uniform diameter filament. So we need to use a single screw extruder before feeding it to a printer. So this was again my other DST grant within which both the equipments were there. So with this funding from ISHRAE, we blended it and then we fed it to a single screw extruder. Now the wire of a definite diameter is possible. And then consistently we fed that, and finally we come up with the Kelvin structure. In entire this process, optimizing the parameters here, that is a mixing parameter, optimizing the extrusion parameters here, and then optimizing the 3D printing parameters here. So when you talk about 3D printing, it's the flow rate, it's the temperature, it's the feed, it's the temperature of chamber, temperature of nozzle through which you are feeding the filament. So all those critical parameters comes in, and above all, once you deposit onto a 3D printer, it should be warpage free. You have a base of a different material, you are printing a material of a different material, then we need to keep the temperature gradient at a specific, within a specific margin. We use a different, basically all these 3D printers comes with a glass substrate, but we use a different materials to make sure that we'll put that on a glass, and so that the warpage is minimum, and whatever such structure. And just see, this is not a solid piece. This is a hollow piece having a higher chances of warpage and very thin structures. So a lot of optimization goes in there. And
just 1 second, what is the PGF and PHM? And this screw extruders and all, they are, I mean, commercially available, these instruments?
Yes, very much, very much. So even we can customize it based on our requirement, but these are commercially very available because these are the basic systems for all the polymer industry. For an example, whatever now, if you might have your 4-wheeler and you will see a dashboard, right? That dashboard is basically made up of an ABS. That is made up of a polypropylene, and whatever framework you see for your speedometer, it is made up of an ABS. So all these things are different color, right? So this different color meaning what they do, they take an ABS palette, they take an, let us say, brown color, they mix it, they extrude in through the same systems, but no doubt the tonnage system, or rather the capacity is really large. Now, whatever you see here, this system is having a 5 kg maximum. Now, for all these automobiles, what dashboard, bumpers, everything is been manufactured, they have an extruder system of minimum 100 kg as an input. So these machines give us small pallets, and these pallets are again injection molded, and that injection molding outcome is that what you see on your dashboard, bumpers, or the drawers in the automobile. So
Okay.
that's how, these are all commercially available based on the
And
capacity.
what is PGF and PHM?
So F is for fiber, M is
Ah.
for microballoon.
Oh,
That's-
okay, okay.
So here it's a glass fiber and hollow micro. This is hollow microballoon. This is glass fiber.
You will understand that we are all from another domain. That's
Yes.
why I'm asking you these
Yes.
questions.
Please go ahead. We do even from our perspective, we do just make mistakes. That's why I just mentioned it here. So that is with GF with the HM. So I think I would have mentioned that here as well. Sorry, I'll just modify that in due course of time. So these are all readily available. Only thing is that how we tune up the material properties, and this is what we look for. So once we design a material, we manufacture it, we take a micro CT. And no doubt, a scanning electron microscopy is another instrument which is readily available, but better and more intricate details I get in micro CT. So this is the same micro CT which doctors use for any advanced investigations when we have a bone fracture and so on and so forth. So I have just shown with defects and without defects. So from this to this, we tune up the manufacturing process. So why these are with defect, you can just see there are some pockets here. But many times, let us say you need more damping. We introduce intentionally these pockets, which are not only possible by the material system. So it depends on the application. But for this application, I was avoiding these pockets. And this is where we get a completely foamed, perfect sample, which can be now going ahead with the Kelvin structure. Then we printed this Kelvin structure and then went ahead with, as per ASTM standard, the experimental evaluation of the thermal conductivities. And you can see all the values here. So this is again glass fiber, hollow microballoon, no doubt with the other additive. So this is 20 is 20 by volume of glass fibers and 70 is the porosity level. So this 20 number decides how much content of glass fiber or microballoon you are adding in the base material. So this is we went ahead with 30 here, and then porosity level is being changed 70 to 80 to 90. And what does this porosity level change? I think I have already shown it here. This is what. Here now the struts are made up of that material with that much additives, but with a different porosity level. So with this, we could able to reach to 0.0311 experimentally. So we were very close with our CFD simulation and analytical investigations. So we went ahead with this just for an example sake, because ultimately the product should come out at the end after doing all this. So this was that product we printed on a 3D printer. So first, this is there is no joint here because 3D printing gives that advantage of integrated component. So this is a vessel which was completely printed, and this was the cap which has been completely printed, made up of the material system of having thermal conductivity of 0.0311. And then I have just mentioned the other parameters because probably this is the parameter which industry looks very closely. What is that cost of entire doing all these things? Printing time is 3 hours for this vessel. The reason being the printing speed maximum was around 20 millimeters per second. Nowadays, it has been increased to substantially because this was the printer which I procured in 2016. So nowadays, printers have higher printing speeds. We can increase that. I have just shown a simple vessel here. You can have any complex intricate shapes produced because we need to just feed an CAD drawing to a printer. But if I want to go for an injection molding, based on a small change, we need to produce an entire new mold cavity there. So that doesn't come in picture. Tooling cost is 0 in 3D printing. And this is what structure is available inside with the foamed parameter, and that's how it gives us 0.0311. Now, this is another slide which all of us want to just compare, benchmark, and so on and so forth. So we compared that. So the cost comes out to 135 as against the best one as PU foam 105. It is flammable, yes, but if we use with puff panel, that can be also arrested. As just like this, we can use this PU foam also in the puff panels. So that's how the final comparison sheet looks like. And this is what the salient feature of this proposed material or the research outcome which was funded by ISHRAE comes out. The material is biodegradable. It has a lower environmental footprint, cost-effective manufacturing of porous foams, and same pellets I can put it into the injection molding and get that as well. Much lower material consumption because now we have a Kelvin structure. No doubt Kelvin structure is not possible in injection molding machine, but because of the Kelvin structure, we are saving a lot of material all around. Easier scalability. Any 3D printer can print nowadays, whichever are available in the commercial space. Geometrically complex structure, different shape, size, and I said zero tooling cost. You just change a CAD drawing, feed it to a printer, your next product is on the shelf. Can be easily bonded. Any available industrial bonding agents can be used, and it's just like a PU foam the way we use it. So with this, I thank all of you for sparing your valuable time on a weekday.
But what about recyclability? Suppose you have this material, can it be brought back into that filament form and something can be done with it?
Yes, I can crush this and again I can extrude the filament. Rather, we did a study with many such materials. So we found that even 3 times if I process, still the properties are not degrading.
Oh, that's good. That's good.
So we crush it, we extrude, we print it, and we use it. Again, we crush it. So such 3 cycles. The strength drops by around 8% after 3rd cycle, but rest all still goes up. Remaining things still are surviving well. Rather, in one of the study, we compared our 3 cycle what we again manufactured, and we compare with the virgin injection molded ones. Compared to virgin injection molded ones, our 3-timed reused gave a much better performance in 3D printing.
Okay. That's good. So there are 2 questions in the question and answer. I don't know. Can you read? Are you seeing it?
Just a minute. Should go to chat.
It says not in the chat, in the question. Okay, I'll read it out. Is the syntactic foam made of HDPE and infused with fly ash?
Yes. Yeah.
Yeah. And is it?
Rather, HDPE with fly ash, syntactic foams are made with compression molding, injection molding, and 3D printing. Because my students works in the same area. So all these works are available in public domain through publications. Yes, all these have been done.
Yeah, so anyway, we have with us Mr. Vikram Murthy. Vikram, can you unmute yourself to talk? Neetu, can you unmute Vikram? Yeah, so the question was that you did this work while you were at NIT. Is anyone continuing this once you have moved out of that? Are there any colleagues who kind of work on this area? Because we have, I mean, generally in government institutions, once the person goes away, things can just gather dust in some corner, you know. So I wanted to know whether there's anyone of your juniors or somebody who would be.
Yeah, I'll try to get back, but
Yeah.
typically you answered the question. So
Yeah,
it is unusable, I guess, ISO.
Okay, there are some more questions. How these Kelvin structure foams be advanced than PUF foams?
Okay, so one thing would be I would not say much better than PU foam, but definitely looking at the final values of thermal conductivity, those are definitely good compared to PU foam. And one more thing, if you're looking at the structural stability point of view, if that is the question what the person might have asked, definitely we can infuse different pillar systems. Like I have a CNT, multi-wall, single-wall, carbon nanofibers. So at the same time, we are reducing the weight and keeping it more structurally stable. That is possible in Kelvin structure, because ultimately it's a game of, can I able to make a filament out of it? So I have a drawing of an Kelvin structure, we can print.
In PUA foam, you need a foaming agent, right?
Yes.
But here you don't need
Yes.
that. So that's
No,
a
no.
big plus.
Yes. We
Uh,
use like SCO2, but I never used. With the existing system, I could able to look around because of this shell, which is making these voids. That is basically restricting this heat and making it more in a what you can say an insulating form. Yeah.
So, Roshni,
yeah.
Yeah, so
Doctor, yeah.
So, Doctor, I'm very happy to see. My name is Vikram. So,
Yes.
I'm very happy to see your product. And as you said, and Roshni, you asked a question. So, this product is really good for being future ready, because really insulation is all about how much of air pockets we can create within an insulation material. So, that is so much more possible over here. Also, its structural property, rigidity, being able to change its strength, being
Yeah.
able to play with its weight per unit volume, all these possibilities are there. So it is a future insulating material which should be exploited commercially if that is possible. So this was a very good college experiment and product, and we have the output of this project, which is good enough for somebody who wants to explore it commercially, to learn more and to understand more and to do more, because lots of details are revealed in the project report. So I had spoken about this to Lloyd's Insulation, which is a large insulation company. There's one Mr. K.K. Mitra who heads that company's business in Eastern India. And so he showed a lot of interest in whether this can be taken up and this and that. So I told him, you at some time, Roshni, that's you, will provide him with a report of what we have, and then he can explore further and how to take it up with the institute, with Suratkal and all that. Let him only work on all that. But the idea of this insulation material going into commercial production is really something good, not only for our industry, but also for everybody else who
Yes.
uses these materials in automobiles, and so many
Yes.
other applications are there. So I think it has to be, who is going to promote it? Only we can't take it to somebody because we have industry connect. The college will not. The college
Yes.
has done its good work and given us a report. So as we say, no, Roshni, in our research group and in our foundation, it is for us to try to reach out, whatever we do in our research, to others who may take advantage of it.
Yeah.
And we should explain this in forums and things like that, So whatever we have listened to today, we have to see whether we can do another similar one with doctor or with somebody else to explain about this material, because insulation is a very big thing to bring down heat ingress for anything, or reduce it.
Yeah, that's why I was asking him if anyone is left in NIT Suratkal who would continue this.
No, don't waste your time on that. I'm saying it very bluntly.
Rather,
So because we have now whatever is done, so why will those Suratkal do anything further? It's finished, no? That project is over. So an academic institute completes a project and that's it. So we have to see with our report whether any industry application is there to take it up. What else can you do? The institute is not a commercial body to start exploiting it or something.
No, I'm thinking aloud. Suppose our Mitra is showing interest, whether we could have a meeting with the professor also in the meeting if he can spare a little time.
No, that is possible if let the Mitra show interest first.
Okay,
Let him
okay.
first show interest,
Yeah.
and then we will see what to do further. Because the technology and the patent and the intellectual property rights are not with us. It is with that institute. Is that correct?
yes,
That's
it's with
correct.
NIT Suratkal,
Yeah,
even
yeah.
not with IIT Mandi now. But
Yeah.
person being the PI there, I can definitely come on board with you and share my expertise.
Correct.
And I can definitely get connected to whoever
That fellow, yeah.
they want to come forward and take it up.
Right.
Definitely from IIT Mandi side, even irrespective of institute, as
Yeah.
a I'll definitely be there.
Very good. So
And
IIT Mandi is a well-known institute to me. So that's good. Then if we can connect to you, if and when that commercial company shows interest,
Sure,
we
sir.
will take it forward. Roshni, so let's work on that.
Yeah,
Then
yeah,
write a letter to that Mitra,
yeah,
and we will share whatever project report information we have
yeah.
and copy it to doctor and let him respond, and we'll see. Okay.
Okay, okay. So I want to go back to the questions. There are
Okay,
some
fine.
more questions.
Okay, I'm going silent now.
Yeah, yeah. So doctor, it is can use for insulation for chilled water pipe, and how much aging expected? Does it make sense?
For chilled water, I have not, rather, I will not be able to tell anything right now because I did not do any experiments at that level. These were at room temperature to elevated temperature at that point. But because when the chilled water goes in, how the polymer will behave, especially whichever we are using, need to find out first experimentally, and then probably I'll be able to comment on that. But from simulation side, I can just look around and tell you the tentative values, what might happen.
No, sir. This is not a matter of contacting with chilled water. This is he's asking whether insulation on a pipe will it be fine. Of course, it will be fine.
Yes.
Yeah,
Sorry. So
yeah.
I misunderstood. Sorry.
Yeah.
It's possible. It's possible.
Yeah.
Then one more question is there. If my application is solar cold rooms, will these foams play a role in reducing the thermal conductivity? Yeah, I mean, I don't think
Yes.
that's a question.
Of course.
Yes, it's possible.
Yeah. So this material having thermal conductivity resembles to PF only. How can it be commercialized in India based on sustainability aspects? Okay, that I think we have answered.
Yes.
I think that's all the questions. Okay, somebody is saying, is it available commercially? But you should have understood from the presentation that it is not there. What will be the maximum length of molding?
Maximum length of?
Molding. I think there's no limitation, right?
Yes. So it is typically based on the product. So as I said, I was talking about this dashboards of 𝗬𝗧 or Fortuner. Rather, Toyota invited me for their plant when I visit, and that's where I visited there with a huge 2750 tons of injection molding machines, and they were using the same ABS, PP, and color coding and all those things. So here it depends on a product what you want. So here, if I say, as he has asked about dye, I can tell you the dye which they are using for this dashboard of your Toyota Crista Innova. So the mold cavity, in injection molding which has been used is 8 feet tall, 5 feet wide, and 4 feet in depth. And this is the mold cavity which is for your dashboard of Innova Crista. And that comes in the 2 halves. So this total dimension of 8 feet by 5 feet by 4 feet, there are 2 cavities which are merging together. So it depends on the product.
Okay, so I think we are done with it, and I'd like to say thank you very much. Of course, it got a little postponed because of
very much postponed.
Yeah.
Very much postponed. Sorry about that.
No, it's okay. It was a great desire of actually Yash, who had this idea of having these seminars, so it took its time. Anyway, now it's done. So thank you very much. But I think I will be in contact with you for further projects, or
yes,
since you're mechanical and materials engineering, so it's quite fascinating for us.
No, please.
Okay. Yeah.
And heading the department right now, I have a direct access to many people, and if there is a project, as you wrote on the other day, Sunderwell has expertise in that area. And typically what happens, ma'am, is in IIT system, if I am from home area, there is no other person in phone. So if we have 32 faculties, there are 32 areas. as
Okay,
like in
okay.
other institutions. So
Yeah.
each
Uh,
only one area. So
Okay.
I can easily connect if there are any projects to be done, I can connect it to my faculty to you if that deemed appropriate. For
Good,
sure.
good. Roshni, we should think of doing some project at IIT Mandi. So we
Yeah.
will, you connect with him and we will come
Yeah,
up.
yeah, I've already connected with him for
Yeah.
a corrosion project. He's got some other faculty who's interested. So we'll be in touch.
Okay.
Yeah.
And do visit IIT Mandi in Himalaya.
I was
can
asking
host
today
it.
morning, where is Mandi? So I have to search where
It
where
is the opposite end of where you are. But it's a good
Yeah.
place. It's a good place. It's on the way to Manali
Yes,
from,
correct.
from
So
Chandigarh.
Mandi
Yeah.
is known as 𝗀𝗃𝗃𝗃𝗃,
Yes.
and Manali from here, Manali is 2.5 hours.
Okay.
Please do
Good.
visit.
Yeah, yeah.
You know,
We
get
will,
to
we
have
will,
some.
we will. Okay, thank you so much.
Thank you. Thank you.
Thank
Namaste.
you. Thank you, everybody. Thank
Thank
you,
you.
participants.
Thank you,
Okay,
Neetu.
okay,
Bye.
okay. Thank you, Neetu. Bye.
Take care.